Second part, we will explore the algorithm of the association analysis. There are many algorithms being introduced by the researcher, but this is among the popular algorithms, which is called a priori. Okay, being introduced somewhere in 99, back in 90. I can't remember. It was quite some times, a few decades already on the history of the a priori algorithm. But he tried to give us a more systematic way, okay, of how to conduct this task of association analysis. Okay, so this a priori algorithm, okay, try to mine the frequent item sets by the concept of or the approach of generation and test. Generate and test. And then it says that any subset of a frequent item set must be frequent as well. So in other words, if we have this set of milk, diaper, and nuts as frequent, so is the other sets or subset from this frequent item is also frequent. So if I have milk, diapers, and nuts as frequent, the subsets that we generate from this set should be frequent as well. Okay, so in other words, we're trying to say that every transaction having milk, diaper, and nuts also contains milk and diaper. So it is milk, diaper, and nuts. So if these are frequent, other subset is like milk, diaper, or nuts, or any combination of these from this frequent is also considered frequent, right? So and so on. So these are the rules that we will generate by means of the any subsets of a frequent item set must be frequent. But it introduced another property, what they call as the a priori pruning principle, that states that if there is any item set which is infrequent, its superset should not be generated. In other words, it's trying to say that if any of its subsets, all right, that appears to be infrequent, the superset, okay, the superset should not be generated or even tested. Okay, so we can skip that, knowing that one of the subset is infrequent. Right, so that's the meaning of the test approach. So this is the details, okay, on the algorithms. I have to delete or erase that. It's quite slow, right, to use the erase function. But what I'm trying to show is that first we have to scan the database to get the frequent one item set, and then we will generate the length k plus 1. Okay, this is k plus 1 candidate item set from the frequent item set. Then we test the candidates against the database that we have, and finally we will terminate when there's no frequent or candidate set cannot be generated. Okay, so we can terminate. So let's have a look on the step number 1, mining frequent item sets, right? It basically follows a brute force approach that traverses all possible item sets by determining the supports and discards all the infrequent item sets, which is usually invisible. So doing this will create a very huge rules, right, where the items will grow exponentially if we look at all the single items and combination of items. So you can imagine when we involve a transaction in the supermarkets where we have thousands of different products, the sets that we budget will grow exponentially, right? So with that, we need to apply what we call as the a priori property, which I mentioned just now, where we will discard or we will remove, where we will not generate the superset if any item set from that is infrequent. Okay, so this graph shows the computational complexity of the candidate generations. Okay, when if we have the d unique items and we have total number of items that would be to the power of d, so you can imagine what are the possible association rules. If we have on d equal to 6, the rule could be 602 rules. How about if we have more unique item set, it would be even higher in terms of the number of rules. So how we generate the candidates in the a priori, right? How do we generate the candidates in the a priori? So this is the database that we have of 4 transactions. These are all the items that we bought. And remember, we need to have the support mean of 2. So in this case, the first step, what we call as self-joining, okay, of LK, K item set. So to find the LK, okay, we will do the self-joining with itself, okay, where we will denote this as CK. So this is one example. Let's say we have this item set of A, B, C, and E, all right. We will do what we call at the self-joining like this. So we're going to have A with the B, A with the C, A with the E. So this is what self-joinings mean. And then B with the C, B with the E, B with the C, B with the E, and then C with the E, C with the E. So this is what we call as the step number 1, self-joining from one item set to K plus 1 or K equal to item sets. Okay, so this is example of the self-joining. So the second step is pruning. Pruning is basically to remove, okay, any candidate of K item set that is not in LK, not in the database. Okay, the candidate cannot be frequent either, and so it has to be removed. So when we check these combinations, all right, there's no combinations that satisfy the mean support. Okay, so we will remove. So the concept of self-joining and pruning is basically shows how to want to generate the candidates. This is like an overview where we will go to the next slide that I will show the details of how we will perform this, right? Okay, now let's move on to the step-by-step process of the a priori. All right, so we have a database TBD. Okay, the first step is to do the scanning, all right, where we call this a candidate of K equal to 1 item set. Okay, we take out all D unique items. We have A, B, C, D, and E. A, B, C, D, and E. So we have 5 unique items, and we have the mean support of 2. So meaning we will remove, okay, prune the one that does not satisfy the mean support of 2. So 1 is less than 2. So there here we remove it. Then we will produce what we call as a frequent item set of L1. So these are the frequent of K equal to 1 with its supports value, right? So next, we will proceed to the next candidate of K equal to 2. Okay, this is K equal to 1. So now we want to generate K equal to 2, and we say as a second scan. So we do the self-joining, all right, of A and B, A and C and E as I showed just now, and we will get this item set, and we will proceed by counting and looking at the support of each combination. So the support of these combinations is by looking at the combinations of A and B. Okay, how many times it appears in the database? 1 times, this is twice, and so forth. So we will list the support or the counts accordingly. And the next one is to prune the one that did not satisfy the main support. So we'll prune the infrequent item set. So this is considered the infrequent because it doesn't satisfy the main support of 2. How? By checking the occurrence of this one in the database, right? So this will produce the frequent L2. The frequent L2 means here the frequent with the K2 item set. A and C means 2 item sets. So we have generate Q equal to 1. We have generate this is the frequent pattern for K equal to 1. This is this one is the frequent pattern for K equal to 1. And this one is the frequent pattern for K equal to 2. So the next one, shall we proceed? We'll proceed to the next one, where now we want to generate with K equal to 3. All right, so now I want you to generate, all right, what are the L3? Okay, what are the L3 here? We will combine this one and this one, this one and this one, this one and this one, and so on, isn't it? So if we combine AC with, okay, BC, we will get A, B, and C, isn't it? All right. So if we combine AC and BE, we will get A, C, BE. But this is not true because we're just interested to have 3 item set. So we will remove this, right? The next one will be B, C, and E, right? These 2. But in doing this, you have to remember the a priori principle that says the superset, so this is a superset, okay? The superset of the item should not be generated if its set is not frequent, all right? So now, with this in mind, we have to check whether it's subset like A, B, AC, or BC. So this is the superset. Okay, superset is ABC. What is the subset of the ABC? It could be AB, it could be AC, it could be B and C. We check this against the K equal to 2. And we found that AB is not frequent, means not in the list of frequent lists. AC is there, BC is there. But since AB is one of the sets that infrequent, we cannot generate ABC. All right, we cannot generate the superset of ABC. With that in mind, okay, we will only generate, all right, item set of B, C, and E as the next L3. Okay, as I explained just now, we have to do the self-joining between L2 and L2, right? So we do not generate A, B, and C. Remember, A, B, C, we do not generate this one because A, B, and C, once the superset, this is superset, but it says like AB is not here. So we will not generate the superset of ABC. So this is a detailed explanation, all right? And then with that, we will get the support of this BCE, which is 2, all right? So that is how, all right, that is how we generate from K equal to 1, K equal to 2, K equal to 3. And then, shall we proceed? We have to terminate here, right? Because this is the only step that we have produced. Okay, now the first step finished, where we have generate and create the frequent patterns. So the frequent patterns for L equal to 2 is this one. The frequent pattern for K equal to 3 is this one. The frequent patterns for the K equal to 1 is this one. Right, so we have several sets of frequent patterns depending on the number of Ks that we want. So the next steps is to generate the rules. Okay, the next step is to get the rules. So as I mentioned just now, how to determine which rules will be generated. So we have to make use another measures of what we call as the mean confidence. So let's say the mean confidence is given as 70%. So let's have a look on how to calculate this. So remember the confidence of this one, let's say we are interested to look at the relationships between items A and C. A and C, the confidence is given by the support of the combination divided by the support of the antecedent. This support of combination, this support of antecedents. So when we apply rule 1 and calculate the confidence, we will get 1. And if we apply and calculate C implies A, we will get 0.67. If we transform this in terms of percentage, you will get this 100%. This is 67%. So in this case, which rules will be generated? Of course, the first rule, because it satisfies the mean threshold of 70%, and this will not be generated. So this is for 2-item set of A and C. How about B and C, B and E, C and E? So we need to continue to the rest of the possible combination and check out the confidence value and prunes all the one or remove all the one that does not satisfy the mean confidence value. So with that, we are able to generate the most significant rules, right? Sorry, we were able to generate the interesting rules. I cannot say significance because I want to reserve the word significance to the leaf measures, right? That's why I reserve that words. So the confidence basically to find the interesting measures of the relationships between the items, right? So this is for 2-item set. We can continue doing this, all right, for K equal to 3, all right, where we have BCE. So for BCE, okay, is because the way we generate the rules could be depends on number of items with any possible combinations. So we may have rules like B implies C and E. We may have rules of C implies B and E, or I may have B and C implies E. So there's many possible combination, and for each of these you need to find the supports and confidence. But the support is already known as 2, but you only have to calculate the confidence value. Okay, so you can continue doing that. So these are the candidates for possible rules with these 3-item set, and we fire or we remove the one that does not satisfy the mean confidence of 70%. Okay, I hope that's clear on how we should generate the rules under the a priori algorithm. Right, so these kind of things can be performed, okay, in Weka as well. So you can set how many K items that you want to search or want to generate. So it will generate the possible rules with that setting, and then from there we will filter accordingly. Okay, so this is very interesting exercise. Okay, I hope you can explore further on how to visualize the rule set in Weka. Yeah. All right. So the a priori methods brings a lot of challenges as well. So if you notice, when we try to create this kind of things, we have to do multiple scans of transaction database, isn't it? You can imagine it will involve a huge number if we have a lot of candidates, right? It's a very tedious thing. So researchers introduced other algorithms, one of them called frequent pattern mining. All right. So the frequent pattern minings will not be discussed in this session. I'll bring this discussion to my next lecture. All right. So these are the main differences between a priori and F frequent pattern growth. So there's no candidate generation as what we did there in the a priori, but we make use of the depth first searching. All right, instead of looking at the all possible item set, we make use of depth first search by doing the divide and conquer. The a priori make use of the label wise, or what we call as the breadth first search. Okay, this one is more on the depth, or what we call as a depth first search. Okay, that's wrap up the this part. So I have this short quiz, all right, for you to do. And I give you, I think this is a very short question. I only have a few questions. If I'm not mistaken, it contains 8 questions. Um, can you perform? I'll give you around. See how far you can complete this. I think the max that you require will be 10 minutes. You can finish it within 5 minutes. All right, so let's see. I will stop for a while. While waiting for you to answer this quiz. Okay, class? Would that be fine with you all? Can you access the quiz link?
Okay.
Okay, good. Seven questions altogether, actually. Eh? So not more than 5 to 10 minutes should be sufficient. Okay, let's continue. I guess you have finished doing the quiz, right? And you can actually get the results of your exercise. Let's move on quickly to the next case study. All right, so I shall record. Why didn't stop? Okay, there's only a few slides for the last part, which is the case study. So I prepared two case study of my past work. Okay, the first one is on the use of association rule mining method for the identification of the internet use, right? So I provide the link for you to look at this paper if you have time later on. You can read through this. This paper is being co-authored by with other researcher from Indonesia. Right, you can see this is Professor Dr. Wahyu Wibowo and the other co-authors from the University of the uh, Institute Teknologi 10 November. Okay, I guess this is familiar to the Indonesian friends over there. All right, so basically in this case study, we make use of the data from the National Socio-Economic Survey in East Java 2017. This survey is basically conducted annually, okay, by the Statistic Indonesia across 34 Indonesian provinces, okay, and they have selected the East Java province as the study location to represent the Indonesia. Right, and these are the variables of research. So these are all the items, okay, the items being analyzed, and these are the details of that variables. So what are the findings? The findings with the one item set showed that both male and female gender mostly use the internet to access social media. So this is with the K equal to 1. For the two item set K equal to 2, they have found that male and female groups reveal that both genders use the internet for financial services and news. They use there's some other services, but these two appear to be associated with the male and female groups. They further analyzed with K equal to 3, they found out that most male users simultaneously access emails, financial services, and news, right? So with the addition of emails here, okay, just now financial services and news is under K equal to 2, but with the K equal to 3, they further found that the males prefer reading the emails. How about the male? Whereas for the female, instead of looking at the emails, they look at the goods, the services in the internet. So these are some of the findings that they found in that study. Another case study, okay, being done by three of us, okay, on the frequent item set mining to identify the associated multiple SNP or SNPS. Right, so you can have a look on the article link. I provide the link over here if you're interested to read further on the details of the study. All right, been done in 2019. Right, the key researcher here is Dr. Sophie and me and Prof. Azlina. What we did here is that we would like to discover patterns of multiple genetic variants associated with a disease. And we interested to know the T2D disease. I think most of you know what is T2D. It's a metabolic disorder that is developed when the pancreas has problem in producing the sufficient insulin. So we apply the FIM method and the intersection algorithm in a row enumeration strategy. So the one that we have discussed so far is what we call as a column enumeration strategy. The one that being explored here is a row enumeration strategy. So this strategy was chosen to discover the item set from genetic variants of diabetes type 2, okay, which is known as single nucleotide polymorphism. Okay, what are the findings? Or before the findings, there's a little bit on the data source. The data source was gathered from a WTCC. It's a GWAS data set of type 2 diabetes, where we treat the SNP as a categorical data, where each SNP has one of three possible values. Okay, one of three possible values. So we are focusing on chromosome 11 and 16 only. So in human, right, we have how many chromosomes? We have 23 chromosomes, isn't it? 22, we have the same chromosome from 1 to 22. We have another chromosome pattern called X and Y that determine whether it's a male or female. So for this study, we only focus on chromosome 11 and chromosome 16. Why these two chromosomes? This is the most commonly chromosome that associates with this kind of disease. So this is how we represent the item sites in terms of SNP. As the individual as X1 until XM, the combination of the genotypes and so on as shown here. I don't have to explain the details, but what we are trying to show is that we have to explore several values of the supports in discovering the interesting patterns. Okay, so if you look at this one, we try support value of 40, we try support value of 80, and so forth. When we increase the support value of 280, we're unable to generate the frequent item set. Okay, so in other words, what I'm trying to say is that we need to find a sufficient or the correct parameters for the supports to get the interesting patterns. Okay. So what we found here is that when we analyze the item set, so these are the two genotypes that frequently occurring together. Okay, that could be interesting to the scientists that works on the diabetic type 2 disease. All right, so to summarize, the association rule mining is basically to find the frequent patterns, associations, or correlations among a set of items of a in database, where we make use of interesting measures like support, confidence, and correlation, or simply known as leaf. So the notation of S, C, and leaf. And we can employ algorithm like a priori based on the candidate generation algorithm and test to mine and to generate the rules. Okay, so these are the references that I use for this content. Feel free to contact me. All right, if you can email me, you can get the contents in the books that I shared just now and other publication in the internet that I wrote with some other co-authors. All right, so with that, I think that's all from me. I will spend a few more minutes in case you want to ask me anything regarding the topic. All right. So do you find the topic, is that interesting? You think require more explanation? You are free to chat in the chat area over here, all right? So that I'm aware which part is unclear and need further attention. Any question from the international students? So I will switch to my main computer. Okay, class, do you have any question to ask me? Please feel free to chat, to write something at the chat area. Okay, let's move. Let's turn on your camera before we dismiss. Okay, I cannot connect to my Mac, so I just use the tab. So I'm still waiting for any response from your side. Okay, I can see Lokman. Ahmad, any question from you?
So far, so good.
Okay, thank you. Can I have a response from the international student, at least one of you, to on your camera and tell me something or say something before we dismiss the class? Romario, is that you, Romario?
Yes, Miss.
Hi, good to see you.
Yeah, good to see you too, Miss.
So which part of Indonesia that you stay?
I'm staying in Bandung, Miss.
In Bandung,
West Java. Yeah.
West Java. And the class is for which year? You are from what year and which course are you actually?
I'm in 2022 class, international class of informatics, Miss.
I see. All right. So how do you find the association analysis? Is that interesting?
Yeah, so far so good, but like still complicated because so many calculation.
So many calculation. Yeah, that's true. But you will get familiar with that later on. All right. So thank you, Romario. Good to see you, and I hope this will benefit to all of you. All right. If I didn't get any question from you all, I think we can dismiss the class. I thanks for all of you for the participations and your patience throughout the session. I know I break up to so many times, all right, just to make sure that you have ample time to go for a break and so on. Okay, with that, I think that's all. Assalamualaikum, and see you again, inshallah, later on. All right, bye bye.
Thank you, Miss.
Waalaikumsalam. Thank you, Miss.
Waalaikumsalam. Thank you, Miss.
Waalaikumsalam. Thank you, Doctor.
Thank you,
Welcome.
Thank you, Doctor.
Waalaikumsalam. Thank you,
Thank you,
Dokter.
Doctor.
Thank you.
Thank you, Miss.
You're welcome.
Thank you, Doctor.